This is section 2.5, exponential models. So this builds off of the section we did before 2.4 where it was stuff with exponentials. Now we're just going to do a little bit more with those. Equation is exactly the same as what it was in 2.4. So you'll have your y's equal to a is your initial amount, b is your growth factor, and then it's always to the power of the x. Like we talked about before, when you've got graphs that are going uphill, that would be our exponential growth, and then when it goes the opposite way, that would be exponential decay, which they kind of show there, and that all has to do with whatever your b is. And then your y-intercept is always whatever your a value is. So wherever it crosses the y, that will be your a, and that's your initial amount. So there's a couple ways we can do these out. One way is to do it by hand and do some division. The other way is to use your calculator and use there's no O in that, exponential reg. So I'll kind of show you those in those next couple examples here. Okay, so in our example packets, we're going to start with the first one. And in this one, I'm going to show you how to do this by hand. Okay, so it says the population of a certain cell type was observed to be 100 on the second day, and 2,700 on the fifth day. Assume the growth is exponential. Find the number of cells present initially and the number of cells expected on the seventh day. Okay, so what I would do is I'd think about my two values here. I've got one that's 100 on the second day, and then I've got one that's 2,700 on the fifth day. Okay, so what I would do is I would just make little ordered pairs here. So like 2 and 100 as my one ordered pair, and then my other one, the 5 and the 2,700. And then what I would do is I would think about the exponential equation, which is the y is equal to the a b to the x. And then what I would do is I would take these, thinking of them as like x's and y's, put them in there and make two separate equations. So like one would be our y is 100 is equal to a times b, and then it would be to the power of 2. And then the other one there would be 2,700 for the y is equal to a times b. This time our power of x would be to the fifth. Okay, and then what we're going to end up doing with these is we are going to divide them. And if you look back on your note sheet, it'll kind of follow these same exact instructions. So what happens when we divide these is our a values cancel each other out, because just like if it was something like a over a or like 5 over 5, something like that, if something's on the top and the bottom, it can cancel. So same here, since the a is on the top and the a is on the bottom, they can both cancel out. And then now we'd be looking at like 100 over 2,700 is equal to b squared over b to the fifth. And then what I would do is I would kind of keep doing some simplifying, right? So if this is 100 and that's 1,000 or 2,700, well, they both would be divisible by 100, so I could reduce that down to 1 over 27 is equal to, and then remembering when we divide with our powers like this, if the bases are the same, you subtract the powers, so it would be like 2 minus 5. So that would be b to the negative third, or you could just have it as 1 over b to the third. Either way, to get rid of, I'm going to switch that back to b to the negative third. Either way, to get rid of it, you would want to, because our goal is to get solve for the a and the b, so I'm going to solve for the b first. I would do the opposite of this, which would be doing the power of negative 1/3 to each side, which would be the same as like a negative cube root, because since these are opposites of each other, those cancel, and I'd be left with b is equal to, and then I would just do that out on my calculator. So I just type in 1 divided by 27 to the power of negative 1 divided by 3 and that should come out to be a nice 3. So our b would be 3, and then what we're going to do is we're going to use that to plug back into one of our equation there. So I'm going to go y is equal to a, and then I just found out the b was 3 to the power of x. And then to be able to find the a, what you're going to want to do is you're going to want to take one of your ordered pairs. Doesn't matter which one you choose, the 200 or the 5, 2,700, and you're going to plug that in. So I'm going to go the 100 and the 2. So I'm going to go 100 is equal to a, and then 3 to the power of, my x is going to be 2. And then I would take 3 and square it, which is 9. So I'd have a times 9 is equal to 100, and then to get rid of multiply by 9, divide by 9 on each side, so you could either leave it as 100 over 9 to be exact, is equal to a, because that stuff's gone, or you could do it on your calculator, 100 divided by 9, oops, and it's 11.1 repeating. You could also go with that. Either of those would be fine. So that actually answers our questions for like find the number of cells present initially. A is always our initial value, so that would be initial value, or it could be like the amount on day 1 or something like that. Either of those would be fine ways to describe that. And then to figure out how much it's going to be on day 7, what I would do is I would take a 7 and put it in there for the x. So now we're going to go our x is 7, and we're trying to find our y. So I would take my formula still. So y is equal to, just found the a to be either one of those. I'm going to use the 100 over 9 to be exact. And then my b value was the 3 that I found before, to the power of, and for the x, I'm going to put that 7 in there. And then I'm trying to find my y value. So I would do 3 to the 7th, which is a pretty decent number there. And then I would take that times 100 divided by 9. And my y ends up being 24,300. And that would be on the 7th day. That's how many, I think it's cells. So that's how many cells we would have on the 7th day. Okay, back to our other sheet. Okay, so that kind of showed how to do it by hand. Not the easiest thing in the world with the division and the powers and that kind of thing. So you can also use your calculator, which is what I'm going to show you next for example 2. Very similar steps to what we've done before, where we type everything into our lists, L1 and L2, do our stat and our calc, but this time we're just doing exponential reg, and then enter and enter, just like we've done previously. Okay, so if I go to example 2 then, they've got a bunch of information in our table here, and then some questions they're asking. So National Science Foundation publishes info briefs, a newsletter containing brief reports highlighting results from recent surveys and analysis. The following data are contained in the January 2009 article about federal R&D funding. Okay, so we're supposed to use our statistical utility, so our calculator, to graph the data and fit an exponential model of the form f of x is equal to a b to the power of x, which is what we're working on. And for the x, this is an important note here. They want us to use the years after 1990. So they have all the years listed out here, but we're going to have to figure out what all of those are after 1990 and use those instead for our x. And then we can just use the other column just exactly as it is. So the first thing we're going to do is we're going to plug that into our calculator. So like I said, it says use the years after 1990. So the one at 1990 would be 0, 91 would be 2, or 91 would be 1, 92 would be 2, 3, and it should go up to 18, I believe, and every single time it counts by 1. So I would just label that so you got them, so you can refer back to them in a bit. And then those are what we're going to type in for our x, and then the other ones we just type in normal for our y. So you'd go stat, and then you'd go to edit, just like we've done before. I typed them into my calculator earlier, so I've got them both typed in here into list 1 for the L, list 2 for the Y. And then similar to what we've done before, they want us to find our exponential regression for this. So we're going to go stat, calc, and this time we're scrolling down to exponential regression, which would be the one that's got the 0 by it, or like the 10th one. So we hit enter there. It asks us similar questions, so we want our x to be list 1, y to be list 2. I skip the next one, and then if we want to store it, to graph it, if I go this vars button here and then go over one to y vars and then function, enter, and then enter again on y1, that'll put it into my graph, so I don't have to type that in separately. Then I arrow down to calculate and hit enter. Gives me my information out there, so it's in the form y is equal to a times b to the power of x, which is what we wanted. Our A is about 1,625, B about 1.056 or so. So I'm going to write those down. So for part A, our A is approximately equal to 1,625.160, and then our B is approximately equal to 1.056. And then writing that out as a full equation, and they wanted us to round to the nearest thousandth. Writing that out as a full equation, it would be y is equal to, we put our a in there first, so 1,625.160 times our b value, 1.056 to the power of x. Okay, and then B, use our graph, so we were supposed to graph it on the last one, which we'll do in a second. Use our graph to describe how well our exponential curve fits our model. Okay, so what I'm going to do is, since I did that store thing in the y1, I should have my equation in the y1 here. If you didn't do that, you can just type that equation we just figured out there into here, and it'll be similar enough. Then what we want to do is we want to do our scatter plot of this. So we'll go up to either, well, our plot's one there, it'll need to be highlighted, but I would go second, stat plot, and then for plot 1, we want to make sure it's on. We want to make sure it's a scatter plot, and then we want the x list to be L1, y list to be L2. We can hit our graph. Probably not going to show you exactly what you want, so like I was graphing stuff previously on this, so like it's not zoomed in where I want. To get it zoomed in, I would just go zoom and then go down to the 9th one, which is zoom stat, and then that'll give me a much better picture of what's going on here. So my line going through there is the line we came up for our regression line, and then the points are all our points that we plotted there or typed in. So looking at that, it looks like it does an okay job hitting our points. So it is kind of hitting a lot of points there, but there are kind of some low points and there are kind of some high points. So I would say it's pretty good. So I would say for like part B here, model's pretty good, or a pretty good fit. Model is, I'm going to go is a pretty good fit. It's not an awesome fit because obviously you can kind of see that there's some lower spots there and some higher spots there, but it's not horrible. And then they're actually going to ask us to do some finding of residuals, which is how far our predicted points are away from like our observed points. So you can kind of see there that those would have different or higher residuals because they're further away. The ones close to the line would have smaller residuals. So the two specific ones that they want us to look at are 1998, which is the 2,289, and 2004, which is the 3,771. Okay, so what I would do is I would figure out, so our residuals is always our observed minus our predicted. So I would take, and I would take my equation there, plug in whatever information I have. So like 1998 would be 8 for the x I want to plug in, and then we want to see what the y is that gets kicked out. So I'm going to go y is equal to 1,625.160 times 1.056 to the power of, and again, I'm doing this for 1998, which that would make my x 8. And then I just solve that out, so I would just type all that stuff into my calculator, or if I was doing it separately, I'd do that power part first and then times that. And I got approximately equal to 2,513.09. And then to find our residual, just like we've done before, it's always our observed minus our predicted. Observed is the one that's from the table here, so that would be 2,289. And then we're going to subtract away what we just got for our prediction, so 2,513.09. And that ends up being negative 224.09. So that's what it would be in 1998 for the residual. And then we're supposed to do the residual for 2004. So again, I'm going to take my equation. Y is equal to 1,625.160 and then times 1.056 to the power of, this time for 2004 it's 14. So again, I just type that into my calculator, do that power times that value, and I get that my y is approximately equal to 3,484.91. And then again, I'm taking my observed minus my predicted. So my observed in 2004 was 3,771 minus my predicted was that number I just calculated. And that should give me 286.09. So those would be my two residuals. So this one would be below the curve, that one would be above the curve. Okay, so last thing we got to talk about here is half-life. Sorry my dog is being so crazy right now, he's very loud. So last thing we have to do is talk about half-lives. Half-life is basically, usually it's with like some sort of radioactive material or something like that. It doesn't have to be radioactive material, but that's kind of a common thing that they do it for. But it's the time it takes for the quantity of something to decay to half of its original amount. So like if it started with like 50 grams, it's how long it would take to get down to 25 grams. Okay, so the formula for this, it's always going to be our N, which is the quantity of our substance remaining. So after, how many years, how much is left. N sub 0 there, that's called N naught. N naught is always going to be our initial quantity. So anytime it's something and then that naught or sub 0, that's always your initial amount. So that's our initial quantity of our substance. T is our time elapsed, so like how much time has gone by. And then the T sub 1/2 is going to be our half-life of the substance. Okay, so that's what example 3 is, so we'll go to that then. Okay, so a certain substance has a half-life of 24 years. If a sample of 80 grams is being observed, how much will remain in 50 years when only 5, and then when will only 5 grams remain? Okay, so two things we got to figure out here. Again, our formula from that previous page is N is equal to N naught half for our growth factor, and then our power is T over T sub 1/2. Okay, so we got to plug in our stuff that we know here. So for our substance, the half-life is 24, so that's going to go T sub 1/2. So we'll have equals our growth factor of 1/2. We got that fraction as the power. The half-life of 24 goes on the bottom. And then it says if a sample of 80 grams is being observed, how much will remain in 50 years? So if 80 grams is being observed, that's like our original value. So that's going to go in for the N naught. And then after 50 years, so that would be our time. That goes in for t, and then we're trying to figure out how much is left, and how much is left would be our n value there. Okay, so what I would do is I would just take 1/2 to the power of 50 divided by 24 first. So if I go 0.5 to the power of 50 divided by 24, I get that crazy number, and then I'm just going to do that times 80, and I get another crazy number. I'll just round here. It doesn't tell me what to round to, so I'll just make something up. I'm going to round to the thousandths, so 18.877, and then that would be in grams, because that's how much is left. Okay, and then the next one here, this is a little bit harder, but you're going to use the same formula to figure out when only 5 grams are left. So you're still starting with your original 80 grams, but the only thing is we don't know how long this is going through this whole process. So what I would do is I would plug in the stuff I know again. So this time my remaining grams is the n, so I'm going to put that in there. So 5 is equal to, our original is still the 80. Growth factor is still that half. This time we don't know what our time is for the top for that t, so like we didn't know that it was like 50 years or whatever. That's what we're trying to find. So I'm just going to put a t in there, and our half-life is still that 24 years. Okay, so like I said, this one's a little bit more complicated because the variable we're solving for is in the power, but I'm going to show you how to solve that. So what I would do is I'd start by getting rid of my 80. So it's multiplied by 80 there, so to get rid of it, I'm going to divide. 5 divided by 80, I'm just going to reduce it down to 1/16. So if you did it on the calculator, 5 divided by 80, you get that decimal. To turn that into a fraction, you just hit the math button, and then it should say frac. And then if you hit enter, it'll turn it back into a fraction, so 1/16. It's equal to, 80s are gone. Hey! Knock it off. Sorry. 1/2, and then t to the power of 24. And then this is where it gets a little bit tricky. So what I would do personally is I would take both the top and the bottom of the fraction to that power. So I'd go like 1 to the power of t over 24 and 2 to the power of t over 24 is equal to 1/16. Because then what happens there, 1 to the power of anything is just 1, so it kind of gets it away from the top. So then I'm just left with 1/16 is equal to, like I said, that kind of goes away because 1 to the power of anything is still just 1. So now it's just 1/2 to the power of t over 24. And then my other thought here is we could think about this as cross products. So if you remember back to some algebra stuff, what you can actually do is you can multiply the two things that are diagonal from each other when you have two fractions like this and set those equal to each other. So you could do like the 1 times the 2 to the power of t over 24. Set that equal to 1 times 16, which would be 16. So that kind of takes care of some of our issues because now it's not fractions anymore. But then you still have the issue of, okay, well that's to a power, that's not to a power, but there is a way to get that 16 to a power. So what you want to do, since this is a base of 2, you want to try to get the 16 to something with a base of 2. So you're thinking, okay, how many 2's need to multiply together to get 16? So like 2 times 2 is 4, times another 2 is 8, times a fourth 2 would be 16. So 16 is the same as 2 to the 4th power. So if I switch this to 2 to the 4th power instead, and leave that as 2 to the power of t over 24, now since these have the same bases, the bases can go away, and I can just think of this as t over 24 is equal to 4. And then from there, it would just be like a normal problem. So to get rid of divide by 24, we would multiply by 24. That's gone. So our t would end up being 96. Like I said, that's a pretty complex problem there because you've got a lot of steps, and with the power there, that makes it pretty tricky. I think the one on the test would be more similar to the first one that we did, or more of a basic one. That one's pretty involved. I wouldn't expect you to do a whole bunch with that one, so don't get too worried about that. Okay, and then there's just one last thing here to look at. So I didn't talk about this before, but like, so we were doing the half-life stuff. They might also say something about like percentages being deductions. So deductions are basically going away from something. So it would be like, instead, like if you did 100% minus 20%, you would get 80%. So you would use a growth factor of 0.8, which would be kind of like 80%. If they ever ask any questions about that, which I'm not sure if they do, but just good to know. So that's it. Again, sorry my dog was being crazy. Our book page assignment is page 114, 1 to 10.